have been primarily assumed that you have a single cycle processor uh, without any parallel, parallel hardware or without any pipeline in that. So before we conclude the semester, I would like to take a look at some of these more prevalent and more common architecture for which actually code generation needs to be done. So as it would, we would see that, well, while the front end for this will almost not be affected at all, in the back end also, lot of the three address optimization and register allocation, these strategies we have done will still hold good, but with need some modifications. But instruction scheduling does get a lot of impact when we bring in concepts like pipelining or superscalarity or parallel processes. So I'll start the discussion with pipeline architecture. And since we are doing it in the architecture course already, I will do a just quick round and try to highlight issues which need to be handled by the compiler for better optimization and in some cases for correctness actually. So as you know, pipelining is a way of speeding up execution of instructions where the key idea is to overlap execution of multiple instructions. So this is what is commonly known as a data pipeline. So there are a series of data processing units connected, and where the output of one unit certainly goes to the as the input to the next one, and the elements of the pipeline are executed in parallel, or they may be executed in time sliced fashion also in certain architectures. And certain amount of latch or buffer storage is often inserted between these elements. And when we talk about pipelining, it does refer to a variety of pipelining concepts where we will primarily be focused on instruction pipelining for or the data pipelining, which is a basic feature of most of the RISC processors today. But besides that, GPUs have graphics pipeline. We can even in the software architecture, we can have pipelines for commands, tasks, threads, and so on. HTTP accesses have pipelines where multiple HTTP requests go through the same TCP connection and so on. But we will focus primarily on the instruction pipeline. Now, this classical laundry analogy, which I'm sure you have already covered in your course, but just to have a quick recap. So the analogical problem is there are four people who who want to wash, dry, and fold their clothes, where a washer takes about 30 minutes, a dryer takes 40 minutes, and a folder takes 20 minutes of time. So if they do these tasks sequentially, naturally every this washing, drying, foldering process needs 30 plus 40, 70 plus 20, 90 minutes. That is 1.5 hours. So 4 persons will, for 4 loads, will need 90 times 4. That is 6 hours of total time. Now, what we observe is, say for the task of the first person, when the first person is done with the washing and is using the dryer, the washing machine is actually free. So the second person need not wait till the first person has finished up to folding. The second person can actually start doing the washing when the drying for the first person is going on. Similarly, the second person can start the washing when the folding of the first person is going on, because these are independent machines. And at the same time, the third person can start doing the washing. So that kind of overlapping is what is basic pipelining. So in the next slide, we have this pipeline structure. So the first person initially puts in the load. It's only washing the clothes. Then it goes for drying when the second person has put in the washing load in the washing machine. In the third part, when the first person is doing folding, the second person puts the clothes for drying, and the first person starts doing the washing. So you keep on overlapping in this way, and if you see, if you add up these times, you'll find that this can now be done in 3.5 hours comparison to 6 hours for 4 loads. Right? So you can overall squeeze the time significantly by utilizing the idle time of different machines when they're done with one job, and they can take up the job for the other person. So there are two terms that is often used in this connection. One is called latency, and the other is called throughput. Latency is basically the time taken from the start to the end of the job, right? So what is the time I will take to actually get my clothes done? 30 minutes plus 40 minutes plus 20 minutes, which is the drying time. So total of 90 minutes I will need. So as we pipeline, the latency will not change, whether I'm doing a sequential laundry or I'm doing a pipeline laundry. In both cases, my latency will be the same. So that is to be borne in mind, in particularly in contrast to parallelization, when we talk about that, wherein the latency itself could reduce. So here, the time taken to do a single job is not getting reduced, but what gets reduced is the throughput or the rate of production. That is, what is the total time taken for the total set of jobs, which is in case of the sequential laundry. I'm sorry, there's a typo here. In the case of sequential laundry, this was no, this is okay. So if I look at throughput on the average, that is the total time taken divided by the number of tasks completed, then in the sequential case, it was 90 minutes, same as the latency. But in the pipeline case, it drastically reduces to 52.5 minutes. So in terms of the utilization of the system, the throughput of the entire workload is substantially getting reduced, while the latency of a single task does not change. So the few of the other observations that we can make is, what is the rate of this pipeline? What is the rate in which it could put this throughput? Certainly, the rate is limited by the slowest pipeline stage, right? Because that will have to be done for everyone. So here, as we see, the folder has the fastest operation speed of 20 minutes, whereas the dryer has the slowest. So this is kind of the controlling, deciding factor in terms of, or this will give a bound on what is the maximum throughput that we can actually achieve. So as you can see, multiple tasks are operating simultaneously on different resources, as the diagram on the left shows. And how can we increase this speed up? There could be several ideas. One is it would speed up if we had more steps. Like if we could, like in case of laundry, possibly we cannot divide it into further steps because decided by the specific machines and the specific tasks. But in general, the more number of steps we can have, the more number of overlap of tasks by different resources that will be possible. So naturally, the throughput would be better. So the potential speed up that we can get is actually the number of pipe stages. Obviously, we cannot get a speed up more than that because those are number of pipe stages basically tell us what is the maximum stuff that can be done in parallel at a time. So if these pipe stage lengths are unbalanced, like in this case, then naturally it reduces the speed up. For example, here, it will really not matter to the throughput that much if either the washing machine or the folding machine took more time than it is taking, as long as it does not exceed the time for the drying machine, which is 40 minutes, right? So it is good to have balanced length for doing any pipeline design. And also there is in the left, when all these three machines are being used, then you can say that the pipeline is actually full. So before that, you have a stage where you are filling up the pipeline, and towards the end, you have a time where you are draining out the pipeline. So if you have smaller number of tasks, then naturally the overall throughput will get impacted by the share of time you use in filling up the pipeline and draining the pipeline. But for a larger number of tasks, that part will start getting insignificant. Right? So these are some of the basic. So that analogy, which I'm sure you knew already, is just to get us to the basic ideas. Now, the pipeline that we would primarily start using for our instruction scheduling design is a 5-stage pipeline, which is very typical of MIPS architecture. MIPS 5-stage architecture is a very common one. There are more stages also, but this is a very common one. So these are the 5 stages, and it is very important to understand what these stages do. So, and this is a balanced pipeline, which means that every stage works in the same amount of time. So every stage takes 1 cycle. Right? All balanced properly, as we had seen that balancing is a good thing to do. Then we have instruction fetch, or IF, which reads the instruction from the memory, because that's the first thing you'll have to do for execution. It's followed by, you need to, once you have got the instruction, there are 2 things to be done. One is you will have to decode the instruction to understand what kind of instruction it is. As you know, in the instruction encoding, there's a part where actual actions for the instruction is encoded, whether it is an add or a multiply or a load or a jump and so on. And then it might have resource registers involved in that. There may be registers which you need to read for doing this. So you read those resource registers. Both of these you do in the ID stage. Then you have the execute stage, where you, for a arithmetic operation, you compute the register. You try to compute the register type result. For a branching operation, you want to find out what is the branch outcome. Will the branch be taken, or will the branch be not taken? Then you have a 4th stage, which is mem, where you read or write data memory as needed. And in the final write back stage, you write back the result to the destination register if that is involved. So here is a small table which shows, for different instructions, what are the stages that are used. If you have a branch on equality, naturally you have instruction fetch, decode, and execute, where you decide the branch outcome. Naturally, once you have decided the branch outcome, there is nothing to be done in terms of the memory read write or write back. So those stages have no action. So you are done with the instruction. A register type operation, like typical ALU operation, you will have fetch, decode, execute, and then you will have to write that result back. You have to write back the result to the destination register, add R1, R2, R3. So you have decoded add in the ID stage. R2, R3 you have read in the ID stage. You do the addition in the execute stage, and that addition result from ALU you write back to the register file in the write back stage, which is the 5th cycle. If you have a store instruction, then you, after decode and execute as to what you have to store, computing the memory address and so on, then you will, in the mem stage, you will write that in the memory. Whereas if you have a load instruction, Then after the main stage, where you have basically found the memory to load from, you'll have to actually load that value in the destination register. So you need this as well. So these are, these are the most common typical types of instructions in a generic form, and that is the kind of stages that they use. So if we look at this, look at a very naive pipeline processor architecture. So we'll have instruction fetch happening here, then the instruction decode, then the instruction execute, then the memory access, and then the write back. So these are, and since we want that at every stage, we might want that once you are done with one stage, you would like to load another, put in another instruction to use that stage. So the typically between stages, you will have some latch or buffer to keep the result of the earlier instruction, which you can push on as input to the next stage. This is a very simplistic view. So in the instruction fetch stage, you have the memory to fetch from. You have the program counter with its new program counter value. In the decode phase, you have the register file, which is the bank of registers that you have. The control, which is decoded from this instruction as to what needs to be done. So that's the instruction decode. In the execute, the main thing is ALU. Besides that, you will have computing the jump, the branch targets, the memory address, and so on. In the memory stage, you will have the memory address floated from this and the data to be able to read or write from the memory. And finally, in the write back stage, you have the final memory value or directly the ALU value. It depends on, you may, like for load, you are taking from the memory and loading to the register. So this path is followed. Whereas if you're an ALU operation, then you are register type operation, then you directly get it from here. So either of that. So you have a selector here, you have a marks here, multiplex, and then you put it back to the register file. So the reason I'm highlighting and recapitulating on this architecture is because this is a generic representation of the architecture, which the compiler has to keep in mind while it does the code generation and the optimization. So schematically, we often draw it as a pipeline diagram, as in here. For example, I'm highlighting cycle 3, where the load instruction is in execute, the subtract instruction is in decode, and the AND instruction is in instruction fetch stage. Right? Now, similar to the laundry, you can see that if I have 5 or more instructions, then I will reach a stage in the 5th cycle first, where I have the whole pipeline full. That is, all units of the pipeline from instruction fetch to write back are working. So I have a full pipeline, and longer this full part will be, better will be the throughput. And what I have before that is the filling part of the pipeline, and what I have after that is the emptying part of the pipeline. Naturally, if we take this example, then my latency is 5 cycles, because every instruction takes 5 cycles. My throughput is 1 instruction per cycle, because every cycle, at least 1 instruction will get completed. Right? So it is 1 instruction per cycle. And the concurrency is 5, because I have 5 stages. And the cycles per instruction is 1. So this is an ideal situation without considering any of the consequent problems of the pipeline. So these are the definitions of the terms that we will go with. Now, ideally we would expect a CPI of 1, and the speed up should be equal to the number of pipeline stages. But there are several hazards which may limit this, and there are three types of hazards. One is called structural hazard, which is primarily due to the pipeline hardware that it happens. And then we have data hazard, which is primarily in terms of the dependencies or anti-dependencies that you may have in the program, that is more decided by the program. And then you have control hazard, which is also caused by the delay of fetching instructions and because of the control flow, branches and jumps, and is primarily due to the program. So these are the three types of hazards. So a hazard means that there is some condition that has happened so that all instructions that are in the pipeline in the next cycle all of them cannot continue executing. So one or more of them will have to be delayed in the execution. And so that when that situation happens, so we say that we have a pipeline stall. So this is an example of a pipeline stall. Below here on left, you can see that these are different stages of the pipeline. It is drawn in a rotated way. The different stages: fetch, decode, execute, and write back. And this is how the instructions are coming in. So the green instruction goes in to the fetch. In the next cycle, the purple instruction is in the fetch, green has gone to decode, and so on. It's very easy to see how the pipeline is flowing. And on top, at least you'll have, since this is shows a 4-stage pipe, so you should at least have 4 waiting instructions, and you will have eventually 4 completed instructions. Now let us assume that for some reason, the reasons could be many. For some reason, let's say when we are in cycle 3, that is for the decode of the purple instruction, you get into some problem. So I'm sorry, in cycle 2, you get into some problem so that you are not able to complete the decoding in cycle 3 as expected. So what will you do? Your fetching is taking more time. So you are actually extending into the time that you should have used in decoding. Right? You can see the purple is getting extended here because its fetch could not complete on time, and therefore in the next cycle also it is still doing that, which means that where it should have done a decode, it actually does nothing. Right? So this is, you can consider this as a no operation instruction, or as it is often called, this is referred to as a bubble, right? As if the bubbles are coming up where you are doing nothing. And that has a propagating effect. Since you could not do this decode on time, you cannot do the execute on time, you cannot do the write back on time. So you can see that the entire pipeline is now getting delayed. So when this happens, we say that the pipeline has stalled. So if for any reason an instruction is not able to complete the particular stage within its given time, then you have a stall in that pipe, and that has a propagating effect across the entire pipe following this. Now, let us see what are the different hazards that you can have. So first, the structural hazard. Structural hazard is, as I said, it's primarily driven from the architecture. So it will happen when, say, you have 2 instructions in the pipeline, both of which in the same cycle want to use some common resource. For example, you are trying to do a load here. So in the mem stage, you have that in cycle 4 for the load, and you are trying to do some instruction 3, which is in the instruction fetch stage. And as it so happens that Obviously, there will be different memory addresses because when you're loading a data. When you're doing instruction fetch, you're fetching an instruction. But in terms of your hardware, they may be using the same port. If they're using the same port, that is, if your data memory and the instruction memory, in terms of the hardware, has overlap ports, if they're using the same port, then in the same cycle, you cannot read port. You cannot access port. Right? So that would mean that you will have this is what is called having a structural hazard. This is one. I mean, it could be because of multiple different resources, because your memory is a resource. There could be special hardware, which could be a resource, and so on. But this is the basic idea. So if you have that, then you will have to stall the pipeline. I mean, either hold this load instruction to do anything, or this instruction 3 not to fetch in this cycle. So by stalling, that is inserting knobs, you have a very simple solution, and the compiler should be able to analyze the program and decide when the stall is needed. Though pipeline architectures do have dedicated hardware to detect that as well. But the compiler needs to know that model and know about the stall to be able to eliminate that subsequent. So the easiest way to work around this hazard would be to stall. That is, just put a no up and delay one of the instructions as is appropriate. It is low cost, simple, but the flip side is it will increase your cycle per instruction, because now at least one instruction has one cycle where it is not doing anything. So it will start increasing more than less than one. I mean, it will increase your cycles, it will become more than one, right? It can have certain performance effects. So you can have different other types of solutions like pipeline hardware resources. You can have hardware resources also pipeline, which can give you good performance. You can replicate resources for really good performance. So what you're basically doing, you're basically increasing your processing units, but that of course increases the cost. It could increase the interconnect delay, and it's workable for divisible resources, but not every resource is divisible in that way. So these are the different aspects of the structural hazard and its resolution that you. Next, let us move on to where the compiler has a very significant role to play. That is data hazard. This will occur when there are instructions active which need to access the same data. It could be in terms of memory, it could be in terms of registers. Okay. So it is quite possible that you have two instructions, A and instruction B. So the instruction B, which comes later, needs to manipulate, either read or write, a data which A is supposed to also manipulate. But B is sequentially after instruction A, but B needs to do that. So if you had been working with the model we had followed so far, that is, instructions are strictly sequential, and an instruction starts executing only after the previous instruction has ended, there is no problem. But the moment we are in pipeline, B has started executing even well before A has actually finished. So this might violate the order of instructions and actually cause really bad errors. So if we ignore that, then we could have race conditions or race hazards. That is, a data is read before it is written and so on. So there could, as you can easily see, there are possibilities that A can read or write, there are possibilities that B can read or write. So naturally, you have 4 combinations. So the first is read after write. Right? So you have a dependency that A has to write something which B will read. So B must read after A writes, which is a true data dependency. Or you could have a write after read. Right? So you have A is reading something and B will write to that. So basically the violation here is if B writes before A has read, then A will read something wrong. So this is called anti-dependency. This is reversible. And there could be output dependency. That is, A is writing, B is also writing. Both of them are writing to the same location. According to the sequential logic, the value written by B should be the final. But if B writes before A, then A will overwrite that value. That's it. The fourth combination, which is read after read, since both of them are read, is not a hazard. So let us look into these hazards one by one. So let us look at read after write. So we have 2 instructions, I1 and I2. And I've just written it in generic form that R5 plus R3 arbitrarily are added and written to R2. And in instruction I2, R2 is read, added with R3 and written to R4. Right. Now, you can very well understand the problem here, because as we have discussed, the value that will go to R2 will happen in the write back stage, right? Because it is a final update of the register file, which is a write back stage, which is in stage 5. Whereas the value that will be read by I2, though I2 is the next instruction, but the value that will be read by I2 will be in its I2's second stage, right? Which is the instruction decode stage. Right? So if these 2 instructions are consecutive, then in terms of time, I2 will read R2 before I1 has written R2. So this is basically a data dependency problem or a communication problem. The value that you wanted to communicate from I1 to I2 is getting into problem due to this hazardous data transfer. So that will have to be taken care of. So how do we solve this problem? One way could be to let hardware detect read after write. Hardware certainly can detect that because it knows what the instruction is. So, and what are the destination and source registers being used. So hardware can use that logic, detect that there is a raw that has happened, and stop. That is, put knob. So what it will do, if I go back to the previous slide, what it will do in the execution of R2, it will put a knob when R2 is to be written, delaying it, maybe multiple cycles it will put knobs, delaying it to the point when R2 in I1 is actually ready. Right? So this can be solved by hardware also. So now this is low cost to implement. It's simple, but it will reduce the basic throughput of the system. So we have to try to minimize the stalls. Now, how do we minimize the stall? Now, there could be a hardware solution to that, which is quite common, which is called the forwarding or bypassing solution. So the basic idea is that, again, if I go back and look into this I1, R2 will be written in the write back stage. But this addition of R3 plus R5 will happen in stage 3, exec stage, right? So the ALU will already have that value. But it is just that after ALU has that value, there is a memory cycle where nothing happens, and for this case, and then there's write back. Only then it will come to R2. So what if we do a shortcut? That is the value that ALU has after this addition. If we can put a bypass path to, bring it in here, because that is what is going to be the value of R2. If we bring it in here, then we will not need to wait till R2 has been written back. So there's a basic idea of forwarding or bypassing. It's also called shortcuts. Right? So there could be forwarding from execute memory registers to execute stage, or memory write back register to the execute stage, and so on. So let us look at each one of these cases in some more detail. So first is how the hardware can provide a stall. You can see that this is an example of an add R1, R2 being added into R3. And then there is a subtract where R5 is subtracted from R3 and is written to R5. So this is the stages of add. So add will finally have the value of R3 updated in this cycle, cycle 5. If you look at sub, once in cycle 2, it has been decoded. In cycle 3, I'm sorry, in cycle 2, it has been fetched. In cycle 3, it is expecting to decode and get the value of the register. It is not there. Value of the register R3 will be available only in cycle 6 because it is updated, written in cycle 5. So from cycle 3 to cycle 6, for cycle 3, 4, 5, this sub instruction cannot proceed. So what you do, the hardware will fill up with no ops here. And you insert that bubble, and you have stalled the pipeline for the sub, and it cannot proceed. And once you have done that, then you do that for the next instruction as well. For the same reason, it uses R3 as well. So this will stall after the instruction fetch as well. So you will have stalls like this. And if you look in the left architecture diagram, the diagram that I showed, this is just simplified. Then in the instruction fetch, after the instruction fetch, there is a detect hazard kind of unit that you can put, which can check what are the different registers that are involved. This is a destination register. These are the source register coming in. All these different inputs it can take, and you can easily write a kind of a predicate to decide if you are getting into a storm. And if you do, you just insert them. This is the hardware solution. Let's see how does forwarding minimizes this problem. So in forwarding, what it does is in the architecture, you have a forwarding unit. So what does the forwarding unit do? That instead of letting the value read from the register file going on to the ALU, it tries to get the value from future. Because these are the values already computed by the earlier instruction. So you can look at the right here first. You can see add. After add has done, add is worked with, that is R1, R2 has been computed in R3, in the EXE. So here itself, you have the value of R3, though it is not available in R3. So instead of trying to read it from R3, it can directly pass that value to. So in ID, you'll have to do something. In the decode phase, you'll have to do something, responsibility of the forward unit, to make sure that it does not try to read from R2, which is a wrong value. It has not been updated. But the value that it needs for R3 is directly passed on from the forwarding unit to this ALU. So similarly, I mean, after the memory cycle, when the OR instruction needs R3 after the memory cycle, similar forwarding can also happen. So this is an example of from exec or memory registers. How can you get the value, right value, before it has been updated in the register, final destination register, into the ALU to minimize the stall effect. The next slide. The other case will happen in, say, this kind of a situation where you have a load and a subtract after that. You have a load of 20 R8. So 20 R8, you understand, it's a indexed address that we have used. So from this memory, in the load instruction here, from this memory, the value will be read, value will be taken. And in the write back stage, it will go to R4. And then sub needs this R4. Okay. Now, if it since it does not get that value, it will have to wait for that value. It will have to stall. But we can minimize the stall by, after the memory has been read in the mem stage, before write back itself, we can give that value, because we know that is the value of R4 right now. So it just needs to stall for one cycle, but then it can proceed with the execution. Without, if we did not have forwarding, it would have required to stall even in this next cycle before, because it could have got the value only after write back has happened. So that is where ID would have come. You would have got 3 stalls coming in. So this kind of forwarding can reduce. So these are hardware features which also help you reduce the data hazard. Now, much of it can be handled in the instruction scheduling by the compiler. Obviously, you will have to know that exact pipeline model of how many cycles are needed in every instruction, and at what stage the instruction does what. So there's a code sequence which tries to compute A assigned B plus C and D assigned E minus F. So if we are doing A assigned B plus C, you will have 2 loads of B and C into 2 registers. Add them into a third register RA, store that result back. You do the same thing for the next E minus F also. Now, what will happen is when you try to do this add, what is the status of the loading of B? This has got fetched in first cycle, this is in second cycle, this is in third cycle. Okay. So in the fourth cycle, add actually needs to get this value. But in the fourth cycle, it is in the mem cycle, so it is just read the value in the memory, but it has not written it to R. So you cannot get that. So it has to stall. Even in the fifth cycle, it cannot proceed because loading of C into RC is still in the fourth stage. So it has not written back. It has to again stall. So this is, you have to compute the number of stalls. Here you need 2 stalls. So basically, to make this code correct, without assuming that you have a hardware detector for raw and stall, all that you need to do is to, after these 2 load instructions, you need to put 2 knobs, stall, and then only this will work. Similar thing will happen in the next part also. But with the power of our data dependency analysis, we can analyze and see that, well, this load of E, RE has no effect on the computation of the first one. So we can promote this instruction before add. If we promote this instruction before add, then instead of having no op for stall, we are actually having the benefit that it will utilize those fallen cycles. And as you do that, as you promote this on top, you also promote loading of F above this store because they're independent. There's no data dependence, which makes sure that when you finally hit sub, actually your E and F have got loaded, and you will get rid of the stalls. So this is just a naive example. We will do something a little bit more detailed, but I just wanted to show the idea that even without actually having to stall, or even without forwarding, in many cases, by scheduling the instructions in an intelligent manner with the data dependencies involved, we may be able to substantially reduce the stall in the pipeline. Right? Now, so this was about raw, read after write. There are two others. One is write after read. So again, two instructions. This is trying to write R5, and this is reading R5. Now, if you see, there is actually, this is something in the pipeline which will give you error. But this actually is not a data dependency, because the I1 does not use any data which I2 uses, which was the case earlier for the case of raw. But for the case of war, it is writing to some location, and it is reading from some location, and R5 happens to write to that location. So in simple terms, you can solve this problem by calling R5 as something else, R6. Right? You can use some other register. So you would recall that when we were doing Shettin's algorithm for graph coloring, we did add constraints saying that, well, Z cannot be allocated to R1, something like that. So, that kind of a constraint can be put in here, that since I want a pipeline and the distance between these instructions is just 1, whereas I will at least need a distance of 2, because so that the write back can be proper. So what we can simply do is we can rename this into something else. Of course, this will mean that we need more registers. So you can rename this and solve this problem. So this is called more a name dependence problem. This actually is not a truly data dependence problem. And this is called anti-dependence for that matter. Okay. So here the compiler will have to handle it by renaming if required. Obviously, the instruction movement technique that we saw for raw may also work pretty well. It depends on, but the other choice is at least in hardware, you don't need to do anything specific for this, because you can rename and solve this problem. This again is the same problem. Similar type of a problem where both of these are computing the result into R2, and you do not, you cannot let the value written by I2 to be overwritten by R2. So what you need, again, you have a name dependence issue. You can resolve it by renaming. Now, if I go back one slide for war, if you have MIPS 5-stage pipeline, your you'll see that war can never happen in a MIPS 5-stage pipeline. For the simple reason, you will read R5 by I1 in stage 2, whereas you will write R5 by I2 in its stage 5. So this will obviously always, by the basic pipeline structure, will happen later. But there could be other pipelines where this kind of problems can come. Similarly, for VAWA, you will not have, it is not possible to have it in the MIPS 5-stage pipeline because, again, the write always are in stage 5. So obviously, the write of I2 will happen after write of I1, even in the 5-stage pipeline case. So the basic requirement of the sequentiality will be maintained. But that may be more complicated pipes where these cases will need to be handled. Okay, let me stop here. I do not want to start discussing control hazard because it will take some more time, because that's more critical to understand. So let me ask if you have any questions. Yes. All of you already knew all this, right? This has been fully covered in the architecture course.
About 80%, I guess.
So all that we are trying to, all the time, I just wanted to create a uniform baseline. And what is important is to can out from this, particularly the actions that our compiler will require. So what we have got so far is the need for either actually inserting no ops to create stall, or to smartly reorder instructions in the scheduling so that you can utilize those no op cycles by later instructions being done earlier, obviously not violating any of the data dependency issues. So we will continue on this on the control hazard as well. And then we'll see how different techniques, particularly continuing on the loop, how a technique called loop unrolling and techniques of branch prediction can actually help create efficient code in a pipeline situation. If there are no questions, then let me close here. Thank you very much. Have a nice day. We'll meet in the morning.